Hello, everyone. Welcome to part 2 of our meetup. I'm Josh. I'm from the backend engineering team. I've been a member now for 3 years, I think, just about 3 years. It's been a pretty exciting ride. And this talk basically grew out of some of the changes we noticed crystallizing when we rewrote our database from version 1.8 to 2.0. And that is basically summed up in the title by this word of inference. What is inference, and what does it mean in the new version of our database? I think it's that one. There we go. So what's inference, right? So if we look up a Wikipedia definition, which is an official dictionary now, it's the process of making conclusions from set of premises. So you know something, and then you use that knowledge of something you know, and you make a new deduction. But if we think about what that really means, it's really broad, right? It could pretty much mean any kind of thinking we do, any kind of process that happens in our mind is basically inference. It's always what we do. And if we look at that, use that lens and inspect what happens in TypeDB, we actually find two distinct types of inference. And what I mean by that is we have two engines explicitly doing inference, one of which is a rule inference engine, which we've just had a public presentation that kind of relies heavily on it, and the other type, which is a lot more subtle and less user-facing, is type inference. And if people are coming from the programming language world, this might be a familiar term. And so what this talk is going to be about is both of these topics and how it helps you as a user when you're developing in TypeDB. So what's rule inference? So to answer this, it's kind of already been given away by the previous talk. But what's a rule? Well, a rule is a piece of deductive logic that we encode into the database. And we do that with this construct that we call rule. And it has two parts, which is a premise, the condition, which is encapsulated in this when body, and the then of the rule, which is the conclusion. And the process of rule inference is really the process of finding the rules that apply to situations in your data, that match the conditions of your data, and then when the conditions are met, we perform an inference and apply the conclusion that's written in the then of the rule. Now, the way I've written that definition, where the input is data to the rule, right, so find some data that matches the rule, and then in the output produce some new data that didn't exist before as your conclusion, we can kind of start seeing that looks a bit circular, right? Because the input's data and the output's data. And that's actually something very natural to do in our system. We tend to end up with long inference chains and recursion really, really naturally that just emerge when you start declaring how your system should behave. What are my invariants? Which deductive pieces of logic do I have? And you'll find very quickly they start compounding and working off each other to provide emergent behavior. And so to model this, I think the best thing to do is go through a little example. And the one I've picked up here is a permission system, because a lot of people developing platforms or doing security or building cloud platforms, all of these things, applications, e-commerce, there's a lot of permissions you have to check whenever you build a system. So you often have a user, you have users, you have teams, and you have resources you want to manage access to between the users and the teams to a set of resources. Now, the reason I've picked this example is actually, we have this example in our company. When we built our own CI system, we had to model GitHub set of permissions about who can access what repository, who can push commits where, what are you a collaborator of. All of these scenarios have to be modeled in our CI system to monitor events and see what pages you can access in our internal CI. And what I'm doing here is a very simplified version of that, which has just 3 entities. And those 3 entities in the rectangles, because it's to be red on a projector, are resource, which is our concept of something you can access. And we have teams and users as our primary entity building blocks. To the right of that, we have our access relations. So what these are basically are the indicators of who's allowed to access which resource. And these might be explicitly granted by a database admin or some kind of other administrator to the system. And that person might come along and say, yeah, this team's allowed to access that resource over here, or this user is explicitly given right access to this resource over here, maybe because they are a close collaborator of someone working on it. To extend that, to make it a bit more interesting, we've added 2 more concepts, which are also really common in a model of permissions, where you have a team membership permission, relation, where a user can belong to a team. And on top of that also, we have resource ownership, which forms our last relation out of the set of things we want to model here, where teams or users can also own resources. So there's kind of three main components. We have access relations, which could either be read or write. We have team memberships, which are between users and teams. And we have got resource ownerships between either users or teams and resources. And on the very right-hand side over there in blue, in the oval, we have a permission, which is an attribute in our matching Dixit's representation of schemas here. This is a permission that we're just going to put as a string to make our querying a bit easier. I'm basically treating it as syntactic sugar, and you'll see that a bit later. But that's an attribute on a relation. The fact that you can put an attribute on a relation isn't something you see in normal databases, where you have like a relation as a binary edge, and you can start attaching things to it, whether it's relations or attributes or whatever you want. But I'm just going to take this as granted, something we can do and build on top of throughout this talk. So that's the schema. And what might we want to do with this, right? So the simplest question we can ask is basically this kind of query. It's a match between find me some users, find me some resources, and when they have an access relation, check the permission on that relation, and just report to me the kind of the triples, the groups of users, resources, and permissions. And this should basically come back when there's a permission. It should tell you what permission the user has to this data. Now, when we look at this schema, there are some things we might want to start inferring, right? We might want to say, actually, yes, there's explicit access. If you have an explicit access relation from yourself to a resource, you can read it or you can write it. But maybe if you're a resource owner, you're more like an admin, right? You should be automatically granted the right access to that resource. And maybe if you're on a team as a member of the team, so a user can belong to a team, and that team has access to a resource, you might want to borrow that access to go away and read that document. Or if you're on a QA team and you belong to a QA team and that QA team has some servers they use for testing, you should go be able to use those servers without having someone to go in and copy all the access rights from the team over to you. Because that's basically how you might do it if you were to hard code it in some application logic or in another database. You might start making these brittle connections that mirror the logic of one thing in multiple different places. Yeah, so let's just talk about what a user might be able to do, right? So a user might be able to, for one, follow the explicit access relations they've been granted. So like I said, if an admin's come along and said, yeah, I can access that server over there, I should be able to access it, no problem. And that's just going to be inherent in the data that's written to the database. A bit more interesting is what I've already touched on, which is if I'm a member of a team and that team has some kind of access, even if I don't have direct access, I should be able to have access to the resources. And that applies for both the read and write, depending on what the team has. So these are a user's particular instructions, right? What is a user allowed to do, just in plain English. And on top of that, there's what I'm calling guaranteed rights. So like these are the invariants in the system, further invariants. And that's what I also said already, which is anyone that's an owner should automatically have write access, right? Because if you're an admin and you're the one that can delete the thing, you can probably write it and you can do whatever you want to it. Now, the way I've worded it also, that means that since resource owners can be teams or users, both of them have access should get write access depending on if they're the owners. And also, if you can write, you should be able to read, because how can you do one without the other, right? So in one direction, it should always hold. And this is another invariant we can see pretty easily that we also have in Unix. I think it's where you can't have write access without read access. And some other thing. I'll get my security friend in the back to correct me on that later. Okay, so let's start translating these into rules, right? Because that's what we're interested in. I want to do a little demo of how a real-world situation that we've got in a more sophisticated system in our backend, in our company, might look in a simplified version that is more applicable broadly. So the first two are explicit relations that would have been persisted to the database, so we don't need to do anything fancy with them. But the other two, we can convert into rules. And the rules will actually be very simple. So it basically says when you have a user, well, you have someone that's a member of a team, and that team has a read access to a resource, then that user has access to that resource directly. And we have versions of that for read and write. And this is basically what we mean by borrowing. We're saying, hey, I'm over there. I have access to this team's resources, so I have access to this resources invisibly or like directly, and we should be able to treat those as the same concept. Now, the other access rules, we have things like this, which are really quite simple once you start looking at them, which is the ownership should turn into a right access. And that's just like literally a two-line rule where you can say anyone that has a resource ownership has a right access to that resource. And lastly, we have this last condition we want to model, which is having right access can choose your read access. Now I want to just bring back the syntactic sugar that I mentioned at the beginning with the permission label. We're going to throw that in here and produce 3 rules, which look a bit like this. When you have a relation that is an access relation, if it's a read access relation, you're going to have to tag read permission to the relation. If it's a write access relation, you add the write permission. And if it's a write access again, you also add the read permission. And that's how we're going to get the duality of a write access always guaranteeing you read and write. So really, what we've done is we've very straightforwardly translated an enumerated list of everything we expect to be true into a set of declarative statements that we give to the database, and we've offloaded all the work associated with that and coding it up into the database and don't have to worry about it at all. Let's play with this, right? Because that's what we still want to see it in action. We still want to see it going. So we've got some basic data. We have one user, we have one team they belong to, and that team owns a resource. There's nothing here explicitly in the data that grants access from the user to this resource. But because we're all very good inference engines up here, we can immediately see that we expect this user to have access to the resource because they're a member of a team and the team owns the resource. And if we run our query from the beginning and visualize the answer in the brand new TypeDB studio that Alex is developing, we get these really, really nice looking outputs where we say, actually, yes, that is correct. There is a write access relation from the user to the resource. And this relation has 2 attributes, which are the syntactic sugar I mentioned, with read and write permissions. So that's exactly what we expect. I've left a bunch of space on the bottom here because I want to show you how we can fill in the gap between the starting data and the answer we get out. And this is very similar to what IBM is using quite heavily in explanations. So what we end up with now, if we try to explain where did that write access come from, right? Why does this user have a write access? We can ask the system to basically investigate itself and query, find me how this write access was generated. And it returns not just the answer it started with, but a bit more information, which is, you need to know, if you need to know this, you also need to know that there's a membership to a team, and that team has a write access to this resource you're looking at. But it's not quite done yet, because actually that write access was not even in the data itself. It depends on another inference. And if we explain that, we see that we get back to what we call base facts, or something, the user's data ultimately. We see that this whole picture is completed in that we joined up the original data we started with to the answer via all these layers of explanation that we saw in between. And to do all this, we had to code no logic, right? Well, we coded the logic of what should be true, but we've not said how to do it. And that's kind of the power of declarative rule-based reasoning. Right, and then let's say you come along and now you're trying to generalize your application or change something, and now you can be part of teams which belong to other teams, which might belong to other teams in some kind of hierarchical organization structure. And the way we model this in a rule is actually incredibly, incredibly easy. We just add one transitive membership rule that says if you're a member of a team and that team's a member of another team, you also belong to the team over there. And just by adding this one rule, it'll automatically mesh with the other rules we've written that grant, for instance, borrowing rights to a team that's further down the road, right? So by adding this one rule, I can say, actually, I don't have explicit access to that resource over there, and my team doesn't, but my team's team does, and therefore I have access. And this will transparently integrate with other rules. And just by adding one rule with no more code, very simple change, we've added a whole new feature on the fly. So I'm kind of like evangelizing rules here, so I feel like I should be quite explicit about why rules are so good. So one thing that's a bit more subtle than the a very explicit point we've talked about is that the schema in TypeDB is really going to be, or going to end up looking a lot like a centralized store of domain knowledge. In our backend system, our CI system, the schema is quite big. It's probably 1,000 lines or so long, if not more. And if I look into okay, here's a set of rules that deal with permissions, I can already start to decipher what the application's doing without reading any of the application code, just by looking at the types that are defined and the rules that it's expected to interact with. And just by having the structure and the logic in one place, we start to see a centralized store of knowledge. As we also just saw, it's super easy to update your logic, right? Because you haven't written any logic, you've only written declarations of what the logic is. And so if I just want to go and change something, say, actually, you can't borrow write access anymore, we'll just delete that rule. Or you can only borrow write access if you have an expiration date that matches the current year. We can just delete the old rule and update it with the new requirements. So it becomes super easy to progressively change your rules and your logic because the rules don't store any state, they're just one declaration. And it reduces friction to you as a developer when you're trying to reflect new changes. So kind of related to this is you get to delete lots of application code. So we actually have seen cases where someone writes an application and then they use TypeDB and they realize the application doesn't do anything anymore because all it needs to do is run one query. So we've actually seen cases where people basically want to connect their web browser, which runs the user's front-end code, directly to the server, the back-end database server, because there's nothing to do in between, right? There's no logic anymore. There's no more constraints to check, there's no more model to enforce, no logic. It's all running in the database just by being encoded in the types and the rules. So it's not safe to do that, so they put something in between. But it is possible on some of the smaller apps, and it just shows you how much less work you have to do as a developer. This one's a bit more subtle, and I haven't really talked about it in the previous slides, but building an inference engine is not easy, basically. So building it on the application layer, if you're trying to emulate something like this, it gets really hard to start dealing with performance and transactionality at the same time. So you can build some kind of maybe ad hoc reasoning engine that can kind of do something slow, but because it doesn't change that often is okay. But if you start to deal with it at the database layer, you can get all the benefits of ACID transactionality. So you get to maintain integrity, you get to maintain all of the data constraints, and you get the performance because the system has so much more awareness of where the data is, what the transactions are that's happening, and we're going to move more and more towards sharing work across transactions. So it's faster and faster, even across transactions. And lastly, as we saw, you can use explanations to start to audit why a decision was made, which is immensely valuable for obviously reasons I won't tell you now, but it's in many domains, people have the same requirements. And one of the cool things we bring to the table now with 2.0 releases of reasoning is you can explain all possible reasons that something is true, right? So we no longer have this find me one reason it's true. You can find all the reasons it's true and iteratively peel back this is true because of all of these reasons, and that's true because of all of these reasons. So in our concrete example of permissions, if I had a transitive permission rule that said you can borrow your team's permissions, if I'm a member of two teams that is a member of one parent team, I can find an explanation that explains my permissions this way or that way around, and we would get both in the explanation model. And as a bit of inspiration, there's some use cases. We've got logistics, we've got fraud detection, pattern matching and pattern detection in general. We have data aggregation and augmentation, meta modeling, all kinds of fun use cases, even robotics use cases. So I'm hoping this kind of list of cool stuff is a good inspiration for you to say, in my domain, actually, I might have some uses for rules, and I can simplify my apps as well and gain the benefits of the flexibility and the power of rules. So part 2, that was all rules. I hope that wasn't too unfamiliar given the previous talk as well, and a bit more color to how it might apply in a simpler system as well. But type inference is the other part of inference. So we have rule inference and type inference. It is disconnected, so let's park the previous thought train and start a new one. and start by defining what type inference is, right? And it's basically given a program. Anyone here that's programmed before, you declare variables in your program, and oftentimes your compiler or your IDE or something can tell you actually this variable must be representing an instance of this thing over here. And you'll see this all over the place in programming languages. It's quite an old field. It's as old as programming language design itself. And what the benefit is, often you can do these detections before you actually execute the program. And usually you don't see this happening until you have an error, or you try to like investigate a bit, like, hey, IDE, tell me, what does this variable represent? In a classical programming language, you might have something like this, right? So you might say, let me assign a variable, so semi-classical, more functional these days. You might have a value that is the assignment of 1 plus 1, which are both doubles. And you might have some rules that say, when you add 2 doubles, you get double out. And the compiler, when it compiles the code, will say, yeah, sure. And it might use that information later to say, I need to reserve space for 1 double for runtime when the program executes. But what are types in TypeDB? Well, it's kind of in the title, and I borrowed some slides from Heichel's original presentation on the introduction of TypeDB. The types in TypeDB are all going to be subtypes of these kind of base cases that we provide you when you open the database, when you start the database. So your types will either be a subtype of an entity or a relation or an attribute. So like in our case, we have resources and permissions and access relations, stuff like that, and also roles. Excuse me, that's the beer. Okay, what does a type inference engine do on a query? So a program for us is a query, right? There's no distinction between programs, really, from the way we see it. The queries we get are programs. And if we apply the type inference process to this, which is annotating the types of each variable, we might get something out like that. So if we go back to our permission example, we might be able to deduce that the owner must be either a user or a team, and this $R variable must be a resource, and also that the relation you've indicated is your desired type actually can be narrowed down to something much more specific, which is a resource ownership. And basically what it does is it extracts information from the other parts of the query to narrow down the scope of what each variable can represent. So what's this useful for, right? What can we do with that? Well, just like in a normal programming language, the compiler can yell at you when you do a plus 1. In our query language, we can say, actually, when you try to query for a permission, which you've defined to be a string in the schema, and you try to check, find me the permissions that equal to the value 1, which is a number, or a double in this case, I can't actually find a single type that makes this true. You can't satisfy this query. And actually what we do now is we tell you this is an unsatisfiable query. Most likely because you've made a mistake. And it also doesn't make sense in the schema you've written. And if we start digging into this idea more, actually the bigger your schema grows, the more nonsense queries you have. Because the number of connections you're not allowed to do between things in the schema are really large compared to the ones you are allowed to make. And just in the super simple schema that we had for permissions, all of these are actually unsatisfiable queries. So in one case, we have a mismatched value type between a permission, which is defined to be a string, and assigning it to be a double. We also say, find me an entity with a permission. But actually in our schema, there are no entities with attributes at all. All of our attributes, our permissions, were always on relations. So this is actually an unsatisfiable query that's reasonable as it looks, right? In the next example, I've mixed up roles. I've used one role from a readable access, read access relation, and I've mixed another role from a write access relation, but they can't ever coexist in your data. So we can actually say this is never going to be true. It's totally unsatisfiable in your model. The last one, I made a mistake that most of us in the team at least have made before, which is just swapping two variables by accident. We're saying, find me an ownership of a resource, but then accidentally written the roles the wrong way around and said, actually, we're looking for a resource that owns a team. And this is just an error, right? Now, this is more powerful than you might think. And the danger in it is that if you don't have a strongly typed query language and a good inference engine, these queries will just run and return no answers to you. And not only is that dangerous, because it makes no sense in your model. You've never allowed a permission to be a number, right? You've never allowed an entity to have an attribute. So querying for it in the domain makes no sense. And if we're in the business of trying to make machines more intelligent, to understand your domain better, it should yell at you if you're doing something that's completely nonsense. So that's what we can do now. And secondly, more dangerously even, is you get a really subtle bug, right? If there's already a normal state where you can get no answers to a query, you might never notice that you've written the wrong query. You might proceed as normal, saying, actually, yeah, this user is not allowed to access that resource, or that one, or that one, or that one. And the user's going to be like, why can't I access anything? It's because you swap the roles around in a relation. If you don't have an error detecting mechanism there, this application might run for a long time before you catch these really subtle bugs. So what we do with type inference is you can catch a whole class of bugs that would be really nefarious to you otherwise. And the way I like to think of this is it's like not coding in Python anymore, right? So in Python, you'll run a bunch of code and it'll do something completely wrong and you won't know until it puts out the number at the end, which you expect to be a number, but it actually says hello world, right? Like it just does something that doesn't make sense because there's no error checking and no catching in the middle. And why is that useful to you? Well, it saves you much of time and it makes the language more safe, which makes you trust the system more, which is part of the pitch of TypeDB, right? Like having strong types in the database makes you more productive and it's a safer ecosystem to work in. Okay, so what else can we do with the annotations on the variables in the query, right? So we've done all this work, we run some type inference engine, we figured out that owner and R and these relations can be narrowed down to be more specific types. Well, what we can do with this is we can actually use it just like a compiler would use it for memory layout optimizations. We can use it for query optimization. Because what we can do is we can say, well, if we know this variable is only going to ever represent a user or a team, we can start to look up the statistics of how many of those there are, and the query planner can say, actually, this is a really cheap place to search. Let me start my search here and do other things later. And similarly, in the traversal engine itself, because all of our types and all of our instances are automatically indexed by virtue of how we store them, we can skip things that don't match the types we look for. So that also automatically gives us a speed boost. And to make this super clear, let's do a little scenario. Oh, it's quite small. We have 100,000 data points in our database, of which there's 100 teams, 1,000 users, 20,000 resources, which are owned by one team or user, and 70,000 relations in general, just arbitrary types of relations. And if we don't have type inference, what we end up with is just executing this query as is, without any more information. And you might choose the best way to execute this is to scan all 70,000 relations, because you know nothing else. And for each of those relations, you have to check the roles. Is there a role for owner and an owner for a resource on each of them? And you end up with about 200,000 checks you have to do. A lot of these will read from disk, so it's really expensive. Compare that to with type inference, where you have more information. You can actually narrow the type of the relation and the type of the variables. And in this case, the best way to execute it might be to start from the owner variable, which only has 1,100 possible instances between the team and the user. And then for each of those, we just need to check the existence of a relation that is actually not a generic relation, but a resource ownership relation, of which there's only 20,000. So in the worst case, we end up with 20,000 operations, approximately. And if we start comparing these, we see actually we've done an order of magnitude less work by being able to scope the types from any type down to smaller subsets. And that kind of is the use of type annotations and query runtime. So type inference is both for safety and for optimization. And on the optimization front, really what it does is extract the maximum amount of information and propagate constraints from completely unrelated parts of the query that might be 5 relations away, and actually realize it can constrain your variable at the front of the query based on the information at the back of the query, and we reduce our search space pretty dramatically that way. Okay, so we're getting to the end here. I want to recap. So we have rule inference under the umbrella of inference, and we have type inference. And what they really do is rule inference gives you these two things. It gives you expressivity and abstractions. Because expressivity, you don't need to do as much work in your queries, and abstractions also because you can move data models down to the database layer. And type inference gives you safety and optimization. Okay? Now at this point, I'm almost done, but I want to pull back one more slide from Heiko's intro talk. I don't know if you can see what's coming here, but I want to pull this back. And this is the original reason and the original ecosystem around why having a type system is such a great thing on the database, right? It enables things like expressivity and safety and optimization and logical deduction in the database, right? And the type system does all these things. It enables all of them. And I think throughout this presentation, I myself realized really what inference does for us. But what it does is it enhances the ability of the database to do all four of these things. Between rule inference and type inference, we can compound the benefit you get from just having a type system at the database across all of those sectors. So I hope that gives you an overview of both the very user-facing rule engine and the more subtle type inference engine, and gives you some ideas of maybe what you want to play with, and an overview of how these things we're building in the new version have evolved and meet with the new branding of TypeDB, because it is a strong intersection and they compound on top of each other to improve your experience. Thank you.
So questions for Josh?
I've got two questions. I'll start with one. In the first example around rule inference, if I'm a user of, say, 2 teams, can you encode priority into that? For example, if I need write permissions in both of those teams, I only have to write in one. Can we encode that?
Can you repeat the question?
Okay, I'll clarify it first. So you're trying to say you could get permission from 2 places and you want to use it from one place first? Or is that what you're saying?
More if, like, so part of your explain engine says all the different ways that you can get this rule. Can I write a particular rule or inference that says I need them all? I need write permissions from all those teams.
Okay.
Not yet.
We can't do that yet, basically. Yeah. So we don't have aggregations built into rules, essentially. You might actually build it with a negation, double negation, maybe. Come back to that. So the question, to recap, the question was, can you check whether you have permission from all the teams you're members on to access a resource rather than just one? And the answer is not yet. There might be a way to hack it.
You can check for the presence of absence of any team that you don't have permissions from.
Yeah, you could invert it. You could query, find me, if I'm a member of a team that doesn't have access to this rule, it'll tell you that. So you could use that as a workaround. Yeah, as another way of doing it.
Do the match and also the rule functionality support any kind of math?
Right on point, guys. So this is a long-standing.
Yes. Can I write a rule if this thing is less than another thing, then do this? Or
so that,
can I write a query, how many of these things do I have?
So those are 2 questions actually. So the first, basically the question is, do we support some kind of arithmetic in rules or conditional expressions? So conditional expressions you can. So in the when of the rule you can say when this is true in the condition and this value is less than 20, then do this operation, you can do that. What we can't do yet is look up these 2 attributes, compute a value based on them, and then do something in the then of the rule. Yeah. Which we're loosely billing under a feature called arithmetic, but is actually much broader than that. And
it'll come to you next year.
Yeah. So then you could do cool stuff like evaluation of computation based on the when of the rule before the then, and then use the computed value in the then of the rule. Yeah. So that is coming.
A real world example of that is if I have a palm plantation, I have a certain window of time in which to grab that fruit, the palm fruit, and deliver it to the mill. Otherwise, it's no good, right? And that window is, I think, on average, falls to about 20 kilometers around that, depending on the roads and the condition of the roads and everything. So I actually have to have GPS coordinates where they are, where that plantation is versus where the mill is, and then do a computation between them to say, okay, is that near enough or is it not? Now, we haven't done that in this. We actually use APIs outside to give us that information in our system, but it'd be great to do it actually in the, in TypeDB. So, Michael, please.
I mean,
It's on James.
on the back of that, it would be really cool if we could invoke like third parties APIs from the queries. As in, like, if we need to deal with something that is not just basic arithmetic, and we actually want to do some complex computation, just have it like grab this thing, pass it on to these, like, whatever, R, right.
Is this the hot features? This the show, right? Like, the top 5 features requested for the last 2 years coming out
So yeah, that would be pretty cool, but we're not there yet.
Yeah.
Well, we've actually discussed that.
Yeah.
It's actually it's very difficult to actually implement something that does this. This triggering behavior is something that we would love to do, but how do you know ahead of time what's going to be triggered when? Right? We're not even sure that it's computable. We discussed this at length at some point because we wanted to be able to do this.
You do all the reasoning at runtime.
But exactly, because we backward, all of the reasoning is backward chaining, so we do a strictly the least computation we can to answer the question that you asked. So then you end up having to poll in order to do something else. So
The solution actually is to actually not do the arithmetic in the rules, but to introduce an indexing strategy that performs arithmetic. So so indexing basically happens more live as the database ingests data, and rules are triggered as the database queries data. And so the best place to perform arithmetic actually isn't in the rules, but actually during indexing. So you index certain values which are then available during rules. So that's Come again?
Or at the line, like.
You can, but you won't.
Every night run these series of
Yeah, it's just less elegant and less cool. Like,
Which is a big part.
Other systems implement aggregate paths,
Yeah.
which are materialized views based on rules.
Exactly.
So
Which, by the way, like
actually have done it at one load.
if you want to do like aggregate like by hour, by day, you can do that yourself basically already right now onto the database, right? So when we're thinking about, come again? Like indexing arithmetic values, basically, you can already do that right now from outside the database, having like services, a cron job that basically runs on top of the database.
just runs a matching.
So the problem that I have is I've got something where I want to do counts. How many SNPs are on a gene, for example, in a chromosome. And what I want to do is say, give me the count, but give it to me as an attribute. Can you run that as a rule and say, give me count, treat it as an attribute. Give me a sum, treat it as
that's what we're referring to as the arithmetic
but
indexing.
To me, that could be run in runtime, because you'd say, give me that entity, and I want to know the count, but I want it as an attribute. I don't, because right now count kind of ends, and I can't do anything on count, even in Python, even in a script. I'm left with count. I want to say count is $A, but I can't do that.
Yeah, so in general, right now, when people need to do arithmetic, what we recommend, until it's native in some way for indexing and or rules, because they can be overlapping or non-overlapping features, is to basically compute the value they need on the application side and then add it in, and the rules can then, so you have like a two steps. You have find everything you can, and then read the values out, aggregate them, insert it, and then do the second query. Yeah, it's not very elegant. We're going that way.
But that's why, like, so for us, when we are to think about these kind of features, we must not think of like what the user can do as a cron job outside of the database, but basically what's the actual formal solution within the database as a fully cohesive solution.
It'd be so nice to be able to say team, when the team count is 25, do something.
Yes.
If the team count, or if the login is X number of times per week.
So we are going to do that.
Should we end the night early in the
You probably have the optimal number of beers.
But it's about the right time to start programming.
Any other questions? Any on the remote?
And obviously, we find these talks, they can be a lot to digest all in one sitting. So, as we always say, join us on Discord, and then we can continue conversation there, or as we'll be headed up, we can just be chatting there as well.
With all the James.
But also keep in mind when it comes to so to give like a more formal, like, this is the beauty of basically being part of an open source community. Like, open source community isn't like, I don't care about money, let's give all IP away. That's not quite open source community is about. Open source is about collaboration. Open source is about like getting ideas like from the community and building up on each other's capabilities. And as a company working in the open source domain with the open source culture and open source nature basically means like we also give a lot of the community members to have a say in basically how we want to develop things and what needs to be developed, and also contribute to that development. So like all these ideas, unlike a lot of other companies that basically you don't have access to the team developing it, you don't have access to the roadmap that's developing it. When you're part of an open source technology, part of an open source community, you should join that open source community and you should try to voice what you want. You should try to find other people who want the same things that you want. You should try to contribute these features, and you might also be able to help the developers in the community in the team to actually get those features developed a lot further along, right? So there's a lot there that as a user of an open source technology that can benefit from an early stage innovation, right? Basically, like when you're introducing something new in a subfield in science, in a subfield in computer science, it's almost impossible for any team, not just our team, any team, like right now, like 10 people, we can multiply that to 100 people, 1,000 people to really take on like all of the core problems in that field, right? And to do things, to push progression, like to progress a subfield in that way actually requires a large group of people to actually collaborate. That's what we're starting to see now in the open source community, but like for those of you who aren't yet and having this kind of thinking and questions, like that's what the open source environment that we've created is for, basically. Yeah, so have that in mind when you're thinking about these things. Yeah.
I would second that, because what they don't know is that IBM is probably one of the largest open source contributors out there. If I look at all the contributions we make around the world, in various open source communities around the world, it's massive. And actually IBM gets a lot from that as well in return. So it's not just a one-way traffic flow, it works both ways.
All right, thank you so much. First of all, to Joshua.